Good morning, everyone. Very happy to have you back. Wigderson here again. Today about something completely different, dimensions and regularity. You remember that on Thursday he's also talking towards Steiner.
Okay, thank you, Edith. Thank you, everyone, for coming. So I want to tell you about species dimension, and in fact, this red S, so it's about different notions of species dimension and how it relates to regularity. Eventually, I hope to say some stuff that's joined with the Gishboliner and Asaf Shapira. But for a while, I'll just give you some nice background, some cool, pretty proofs of theorems that I hope you will enjoy. Okay, so the talk, eventually I'll get to VC dimension and VC dimensions, but for a bit I want to talk about regularity. So in general, a regularity lemma says that you have some discrete object, and you can chop it up into pieces, a small number of pieces such that all of them are random-like in some precise sense. And now we have these regularity lemmas. So the first one was for graphs, which I'll talk about in a minute, but we have them for hypergraphs, for subsets of groups, for probability distributions, for many different kinds of discrete objects. And a key question that you want to ask when you have this, so you can guarantee that you have a partition into a small number of pieces, which are random-like. And the sort of basic question is, how small is this small? And unfortunately, the answer is usually really big. So then you can try to ask, this is sort of what the talk will be about, can we impose some extra assumptions on our object to make this small smaller? And then the question this leads to is, what does it mean for some sort of discrete object to be structurally simple? And that's where VC dimension will come in. So to dive right in, let me give you the key definitions of graph regularity. Of course, don't hesitate to ask questions at any time. So if X and Y are vertex subsets of some graph, their edge density, d of xy, is defined to be, this is the edge density, it's the number of edges between them divided by the total number of possible edges. And then we say that xy is epsilon regular if, so it's an annoying definition, so I'll write it. For all subsets x prime of x, y prime of y, with the property that x prime is at least an epsilon fraction of x, y prime is at least an epsilon fraction of y, the edge density we see between x prime and y prime is almost the same as the edge density between x and y up to some epsilon. It's the same epsilon. So what does this mean? It means that the edges between x and y look randomly distributed. So in the sense that no matter how you zoom into a different part of the graph, so no matter how you sort of restrict your attention to an epsilon fraction of the left or an epsilon fraction of the right, you'll see the same density of edges up to epsilon as you would globally. And if you don't like this definition, first of all, I'm sorry, but it's somehow, this is in fact more or less the only definition of what it means for the edges to look randomly distributed. So there's this whole theory of quasi-random graphs due to Thomason and Chung, Graham, Wilson that implies that any reasonable notion you could come up with for what it means for the edges to be randomly distributed is actually equivalent to this one, up to, let's say, a polynomial change in epsilon. So this is really kind of the definition. One important thing to stress is somehow, what does epsilon mean? It's like a quality parameter. It's telling us how quasi-random do we look? Like, what's the quality of our randomness? And so it's, of course, the smaller epsilon is, the stronger this guarantee is. The edges are even more well distributed. And the key thing to keep in mind is this is meaningful if epsilon is somehow much smaller than the edge density. So if epsilon is small relative to the edge density, this is really a good notion of the edges being randomly distributed. And then if epsilon is large relative to the edge density, this basically doesn't say anything. So this will be important later, but we really only want to understand this, to think about this when epsilon is small with respect to the edge density. Okay, good. Questions?
So X and Y, we should think of it as.
You can think of it as like the vertex sets of some bipartite graph or as subsets of some, so you have some ambient graph, and these are just a vertex subset.
Yeah, disjoint.
Yeah, let's say. It's not really necessary. This whole definition can be made to work if they're not, but for simplicity, you can assume that they are. Yeah. Any other questions? Okay. So what is this good for? It's good for, because I mean, it's useful for things. So the main reason we care about regularity, maybe I'll put it here, is that it's useful. So one thing you can do with it is in a counting lemma. So let me give you one such counting lemma. This is what people call the induced counting lemma. And it says the following. So if B is a fixed bipartite graph and epsilon is sufficiently small, then any epsilon regular pair XY contains a bi-induced copy of B. So what does bi-induced mean? Bi-induced just means this is really relevant when this X and Y are living in some ambient space. So you have here XY, maybe my B looks like this. That's my B. So this would be B. What a bi-induced copy means is, I mean, you can find a copy that the edges that are supposed to be there are there. The edges that are not supposed to be there are not there. So it's induced in that sense, but you don't care about what happens inside. So like, it's okay if that's an edge as well, or if it's not an edge. So somehow it's induced when you look across and you don't care what happens inside X or Y. Okay? Definition makes sense to everyone? So the theorem says that, so of course, like a random graph will contain bi-induced copies of any fixed pattern. So this says that if you have some fixed bipartite graph and epsilon is small, then any epsilon regular pair contains a bi-induced copy of B. But there's an assumption this is not true. So the assumption I have omitted so far, this is assuming that the edge density is bounded away from 0 and 1. Right, so this assumption is clearly necessary. If I have an empty pair with no edges, then that will be epsilon regular for any epsilon. But of course, it won't contain a bi-induced copy of anything. And similarly, if it's a complete graph between them, then that will also be epsilon regular for any epsilon and won't contain a bi-induced copy of anything. What the induced counting lemma says is that once you're away from this degenerate case, this relates to this thing. Somehow epsilon needs to be small. Like the density, you have some assumption that the density is bounded away from 0 and 1, and your epsilon is sufficiently small, then you can actually find a bi-induced copy of anything you want.
So also be bounded away from 1 minus the edge density?
Yeah, because I care about this inducedness thing, I also want sort of the non-edges to be, so somehow, yeah, so exactly. So maybe I should also say here, also 1 minus the edge density, because somehow I care about both the graph and its complement, so yeah.
Is this one of the reasons that regularity is the only right notion of random?
In some sense, yes. So this is closely related to this Chung-Graham-Wilson theorem that regularity, one equivalent form of regularity is that you have the right number of copies of any fixed pattern. So this is, I called it a counting lemma. There's no counting here, but there's also a counting version of this statement that, in fact, not only do you have one bi-induced copy, you have as many of them as you would expect in a random graph. And that is appropriately, when you formalize this appropriately, is equivalent to this definition, indeed.
Just to understand the quantifiers.
Yes.
Like epsilon should depend both on B and
on the bound from how far away. Yes, that's right. Yeah, exactly.
So if you assume that the density is somewhere between 0.1 and 0.9, then now epsilon
should be some function of 0.1. Yeah, exactly. Yeah. Yes. Good. Any other questions? Okay, so that's one reason we care about regularity, is that it's useful. We can use it to find structures in our graph like we would in a random graph. The other reason we care about regularity is, as I was alluding to, we have a regularity lemma. So there's a theorem due to Simonyi that every graph can be decomposed into regular pieces. So let me state this precisely. So maybe. So suppose we have some equipartition of the vertex set of our graph. So equipartition just means that all the sets are the same size, maybe up to plus minus 1 if you need to worry about divisibility conditions. So an equipartition of a graph is called epsilon regular. So we use the same terminology for all things. So a pair is called epsilon regular if that. A partition is called epsilon regular if for all but and most epsilon m squared pairs ij, we have that vi vj is epsilon regular. So the partition is epsilon regular if all but an epsilon fraction of the pairs are epsilon regular with this definition. And then the theorem, the Simonyi, so this is Simonyi's regularity lemma, is every graph G has an epsilon regular partition into at most m of epsilon parts, where m is some function. But every graph can be partitioned into a constant number of pieces such that almost all pairs are random-like in this sense. And crucially, this is what I was saying about the small thing, the number of pieces depends only on your sort of quality parameter epsilon and not on anything else. So not on the size of the graph or any properties of the graph. Yeah. Any questions? Everyone happy? Okay, so and this is of course extremely useful because basically what it means is that you have any graph, you can just analyze it by sort of understanding random-like pieces in it. And random-like is useful, like it can do things like a random graph can do, such as this. So as I was saying, the question we want to ask is how small is small? So the question is, what is this m of epsilon? And so Simonyi's proof showed that m of epsilon is at most tower of epsilon to the minus 5. So what's the tower? This means 2 to the 2 to the 2 to the 2, where the number of 2's is epsilon to the minus 5.
So can you just say a bit more about Simonyi? I don't remember. It doesn't say anything about the density within each component. And
no, that's right.
So,
yeah.
So it can be all over.
Exactly. And that's sort of necessary because I mean, it's about any graph. So you sort of have no hope of getting anything like, yeah. So somehow when you apply the regularity lemma, like the thing you need to do is, I mean, you have some graph you don't understand, you apply this and now you get that it's decomposed into pieces that are random-like. But of course, like the densities and so on are reflecting the actual structure of the graph you started with. So you still need to solve the problem on these pieces. Like, sorry, you still need to use actual, not like you apply this and then every theorem is suddenly trivial, but it basically means that instead of solving it on completely generic graphs, you can solve it on graphs that have this nice random-like structure. Yeah. But you still need to do something. Like you don't get any guarantees about densities or where that low density pieces are far from high density pieces or something like this. It's just not going to be true. Yeah. Any questions? Yeah. So Simonyi's proof gave this really horrendous upper bound on m of epsilon, this tower type upper bound. I think for many decades, it was a major open problem to try to improve these bounds. But that actually is impossible. So Gowers showed in the late 90s that there exists G requiring tower type number of parts in any epsilon regular partition. So in fact, this tower type bound is just best possible. I mean, maybe up to the constant 5. Yeah, so unfortunately, this proof just gives the right answer. And this means that whenever you apply the regularity lemma, you will necessarily be invoking really, really bad quantitative bounds because just getting this decomposition. I mean, it's important that the number of parts is a constant depending on it, only on epsilon, but the constant is crazy. And so any proof, any application will get similar bounds in the conclusion. And Gowers tells us it's actually necessary in the worst case. So of course, the thing you want to do now is in applications, you don't care about the worst case graph, you care about your graph. And so maybe your graph somehow is better than Gowers' graph. And so you can add some extra condition to get better bounds. So you can try to sort of come up with your favorite conditions. So maybe if your graph is triangle free, you can get better bounds, and no, you can't. So you can say, okay, maybe if I assume even more, maybe if it's bipartite, I can get better bounds, but no, you can't. You can adapt Gowers' construction. So you can say maybe, you know, I impose something like from structural graph theory, like that it's a perfect graph or something. But no, actually Gowers' example also works for this. So you sort of try all the things you might hope. And the only one that seems to work is that if your graph comes from geometry, then magically you can get better bounds. So this is something people started observing maybe in the 90s, early 2000s, that geometrically defined graphs actually do have epsilon regular partitions with only polynomially many parts, which is kind of weird. I want to explain where that comes from. And it comes from VC dimension. So
Describe Gowers' example, like what the...
So it's kind of difficult. I can, but I can tell you the basic idea. So in Simonyi's proof, the reason you get this tower type dependence is it's some sort of iterative proof. At every step, what you end up exponentiating the number of parts in your sort of, you keep track of a partition. At every step, the number of parts goes up by an exponential. Where this exponential comes from is you're doing something, which I won't describe, but you sort of do something in a local way. And then you take the common refinement of all the different things you've done. So you keep pulling out little subsets, and then you replace your current partition by like the Venn diagram that these things define. So that's why you exponentiate. Sort of you did k things, but now you take the Venn diagram, you have 2 to the k. And what Gowers is doing is he's basically looking at the proof, and he's cooking up an example such that when you run this argument, at every step, you actually are required to pay this exponential. So somehow you cook up a construction and you say, what would it look like if this argument was never wasteful? So at every step, I really had to do this exponential thing, and you think about what that would look like. Then the hard thing, of course, is that you have to then prove that even if you had some other way of constructing an epsilon regular partition, you would still need the same number of parts. Like that sort of shows you that this algorithm will require that many parts. But in fact, he then proves that somehow every regular partition basically has to look the same as this one. So it needs that many. That's where it comes from. But it's not easy by any means. Any other questions? Okay, good. So what is VC dimension? Not going to tell you just yet. I'm going to first tell you about fake VC dimension. So eventually I'll tell you what VC dimension is, I promise. So VC dimension, maybe before I get into the details, it's, I guess as many people here know, it's somehow now one of these most important notions in combinatorics, in learning theory, in group theory, in model theory, that sort of captures what it means to have some sort of low complexity. And again, kind of like this notion of random like, it seems that this is somehow the only definition, in some sense. It's sort of, for many kinds of problems, this really captures the heart of what it should mean to have low complexity. So yeah, in a moment, I will define the real definition. but for now, I'll just tell you what I mean by fake VC dimension. So this is the fake VC dimension of a graph G is defined to be the minimum integer D such that there exists a bipartite graph B whose size is D such that B is not a bi-induced subgraph of G. So what this means is that, so throughout this whole talk, I'm just going to be thinking about bounded versus unbounded VC dimension. Should be thinking of G as some enormous graph or some graph that's sort of tending to infinity along some sequence. And I'm going to say that it has bounded VC dimension if there is some fixed bipartite pattern that it avoids as a bi-induced subgraph. So basically so what this means is that if B is not, just repeating the definition, but if B is not a bi-induced subgraph of G, then by definition, the fake VC dimension of G is at most the size of B. So in particular, you have bounded fake VC dimension if and only if there's some fixed pattern that you avoid as a bi-induced subgraph. Okay? So if you know what VC dimension is, you probably don't like this definition, which is why I called it fake. But it ends up being basically equivalent to the real definition, as I'll get to in a minute.
When you're talking about the size of a bi-induced pattern,
Let's say the number of vertices. Yeah. Okay. Yeah. And again, because I only care about bounded, it doesn't really matter because I just care like if there's a constant one that you avoid. So I can say edges or anything you want. Yeah. Yeah.
And so when you're talking about bounded, we are thinking of like an infinite family.
Yeah. So somehow really sort of we're thinking of G as tending to infinity along some infinite sequence of graphs. And B is like some fixed thing on like 10 vertices that we avoid. Yeah, exactly. Yeah.
Why bi-induced instead of just induced?
Good question. It turns out that this is the right thing. Yeah. I mean, like the reason in some sense is that like you could imagine that your graph, your G is the following thing. So you can imagine that this is G, where what you have is between the parts, you have something super complicated. Sort of super complicated is you want it to have high complexity, but within the parts, you just have a complete graph. And then this should be really complicated. Like we should be thinking this is really complicated because like the real information is in what's going on across, and that's super complicated. But it won't have any interesting bipartite graph as like an induced subgraph because of this stuff inside. So I really want to forbid bi-induced to sort of say that I'm capturing this complicated information across and not caring about what's going on inside these pieces. That makes sense? Any questions? Okay. So, right, I've used the word bi-induced twice on this board.
G here is bipartite by itself,
No, so G is an arbitrary graph.
so you don't know what's the partition.
Right, exactly. This example is an example of a graph that we should be thinking of as complicated, despite forbidding some bipartite thing as an induced subgraph.
But when you define by induced, you knew a partition. You did it for a pair, not for a graph.
Right. So sorry. Yeah. Yes, that's correct. So sorry. I guess I never defined bi-induced in a graph. You're right. So bi-induced in a graph means the same thing as it means in a pair. So you can find a copy of the bipartite graph inside your graph G, such that the edges of B are present, the non-edges are not present, but the stuff inside I don't care about. So yeah, Yeah, thank you. Sorry, I didn't say that correctly. Yeah. Makes sense, everyone?
So maybe the intuition is that if you have a random graph,
Mhm.
all subgraphs
Exactly.
will appear there. But if
Yes.
you have something that's very simple, like the empty graph or
Exactly. Yes.
then
Then there will be some patterns.
Line graph, not for bipolar graphs.
That's right. But for example, a random bipartite graph won't contain a triangle, but it should still be thought of as a very complicated graph because it sort of, it has a ton of complicated structure, even though it avoids a triangle as a induced subgraph. So that's some of the reason bipartite is the thing that comes out naturally, is that those are the kind of structures that you can guarantee in any graph that should be thought of as complicated. Okay, so I promised you that somehow VC dimension makes the regularity lemma easier. So here is one very simple corollary. If G has bounded VC dimension, I mean fake VC dimension, then G has a partition into in most m of epsilon parts such that all but an epsilon fraction of pairs have density close to 0 or 1.
And M is.
And M is some function, in fact, the same function, but some parameter depending only on epsilon and not on the graph G.
also on the bound.
Also on the bound of the VC dimension and on how close I mean to 0 and 1.
Wait, if your M epsilon can be as bad as that one, then why do you want to put VC dimension?
It's only a
So
consequence.
exactly. So the conclusion here, I haven't improved the quantitative bounds at all yet, but I've improved the qualitative, the statement of the regularity lemma. So I've gotten a partition where almost all pairs of parts are now either nearly empty or nearly complete.
Okay.
Which is much stronger than what I knew before, where I just knew that they were sort of this random line thing, but maybe had edge density 1/2. Now I get a decomposition where almost all pairs, are nearly empty or nearly complete.
So nearly empty or nearly complete, you might as well assume that they are empty or complete.
I mean, like in the graph, there might be edges there. You can't actually assume this, but indeed for applications, you can, for example, pass to a related graph where you clean this up. Yeah.
Also equipartitioned?
Yeah, equipartition, yeah. Where is the?
I guess all partition.
Yeah, in this whole talk, all partitions will be equipartitions, yes.
What is close to 0, 1? Is it much smaller than epsilon?
Right, so you can make it be epsilon, so indeed you can just say have edge density, let's say at most epsilon or at least 1 minus epsilon. Yeah. So, but I guess, does everyone see how this corollary follows from everything I told you? So the proof of this corollary is you apply the regularity lemma, you got a partition into a bounded number of parts where almost all pairs are epsilon regular. But then by this, if you have any regular set pair, which has edge density bounded away from 0 or 1, you could find a bi-induced copy of whatever. But I assumed that there's something that you don't, there's some fixed pattern that you don't have as a bi-induced subgraph. So that can't happen. So actually every regular pair must have edge density close to 0 or 1, which gives precisely this thing. Okay?
Why would this bound depend on the fake VC dimension then?
It should also depend on the fake VC dimension. That's because in the induced counting lemma, you need epsilon to be small with respect to the pattern you want to find. So if like the fake VC dimension is like, it has some size of pattern that you forbid, you need to make sure that, okay. Given the statement is not completely formal,
Okay.
I guess it's a little unclear. Yeah, but the real statement should actually also depend on on the VC dimension.
Also, there's a term of VC dimension hidden in M of epsilon.
Exactly, yeah. So there's also some dependence here on the actual bound you have on the VC dimension. But again, somehow the way I'm thinking about all of these things is that I want to think of the bounded VC dimension as just being some absolute constant, and I'm going to sort of let other stuff depend on this absolute constant in complicated ways, without worrying too much about it. So let me just make one definition. So a pair XY is called epsilon homogeneous if the edge density is either less than epsilon or at least 1 minus epsilon. And a thing you can convince yourself of is that this is a stronger condition than epsilon regularity up to a polynomial change in epsilon. So this is a really stronger property up to changing epsilon to like epsilon cubed. And it's strictly stronger. So like a random bipartite graph of edge density 1/2 will be epsilon regular, but its edge density is 1/2, not close to 0 or 1. And so what this thing is telling us is that under the assumption of VC dimension, bounded VC dimension, we can strengthen the regularity lemma to get a partition, not just an epsilon regular partition, but actually an epsilon homogeneous partition. That's precisely what this is. So already VC dimension lets us qualitatively strengthen the regularity lemma. But indeed, I actually promised you also quantitative strengthenings, which at the moment we're not seeing at all. But actually, we can also improve the number of parts under the assumption of bounded VC dimension, which is what I want to get to next. But any questions? Okay.
This is a new one.
No. So people knew this in the 90s. Yeah. And in fact, people even knew the quantitative stuff in the 90s or early 2000s. Yeah. Okay, so let me define the real VC dimension. So definition, F is going to be some collection of subsets of some universe V. So it's a subset of the power set of V. So a set S in V is called shattered so let me write this. For all R subset of S, there exists some F in my family such that F intersect S is precisely R. Okay, so this is the formal definition. This is maybe not the easiest way to think about it, at least for me. The easier way to think about it is to think of your F as just a bunch of vectors, 0, 1 vectors indexed by V. So make like a matrix where over here you have your family's F and over here you have your ground set V. So, right, it's like a matrix where we put 1s and 0s, just like the indicator vectors of the elements of my family. And a set is shattered. So a shattered set is a collection of columns, where in this collection of columns, I see all possible binary patterns. So in this collection of columns, I'll see, the L0 pattern and the L1 pattern and 0, 1, 0, and all 2 to the S of them, which is precisely what this definition says. So it says that for any subset, there's an element of my family that when I look at how it intersects S, I precisely pick up that subset. So this R would be the binary pattern I want to find, and this F would be the row in which I see that binary pattern. Okay, so everyone okay with shattered sets? Okay, and finally, the real VC dimension of F is defined to be the maximum size of S for S shattered. So that's the VC dimension. It's the largest size of a shattered set. So
The fake VC dimension of a graph is the VC dimension of the neighborhood.
Exactly. So the relation to the previous thing is for any graph G, so for G a graph, let N of G be the set system of all neighborhoods of vertices. So this is a collection of subsets of the vertex set. So just over each vertex, you write down its neighborhood. You get a collection of these, and then we define the VC dimension of G is defined to be the VC dimension of this set system. But how does it relate to the previous definition? What would a shattered set look like? I mean, a shattered set is a collection of vertices, and it's a subset S. So it's a collection of vertices. So let's call them V1 up to Vd. With the property that for every subset of them, there is some vertex whose neighborhood is precisely that subset and not the other ones. So there's going to be a vertex that's adjacent to that one and that one, but not adjacent to that one and not adjacent to that one. And there's going to be another vertex that's maybe adjacent to that one, but not adjacent to the other three.
So neighborhood does not contain the vertex itself.
Sorry? Let's say it doesn't. It actually doesn't really matter, but yeah, for simplicity, let's say it doesn't contain the vertex itself. Yeah. Yeah, so then for every one of the 2 to the d possible subsets, you're going to get a vertex that's adjacent to precisely that subset and not to the other ones. So what that means is that if your real VC dimension is, let's say, less than d, then there is some specific bipartite graph that you avoid as a bi-induced pattern. And that specific bipartite graph is this one. It's the one where you have d vertices on the left, 2 to the d vertices on the right, and just each vertex is adjacent to a different subset on the left. So the point is, what we have just proven is that, if the real VC dimension of G is at most d, then the fake VC dimension is at most, I guess, d plus 2 to the d, because there's a bipartite graph on that many vertices that you avoid as a bi-induced pattern. But again, I don't actually care about the real VC, I don't care about the actual number, I mostly care about whether it's bounded or not. So if you have bounded real VC dimension, you have bounded fake VC dimension. And the converse is also true. The reason the converse is, yeah.
You didn't define the VC dimension of a graph.
Yeah, that's, sorry, it's just defined to be the VC dimension of this neighborhood set system. But yeah. And the thing that's important is that the converse is also true. So the converse is also true. So if the fake VC dimension of G is most D, then the real VC dimension is the most maybe D minus log D or something. It can be D plus log D, I guess. The reason that this converse is true, so what does this mean? It means that if you forbid some bipartite graph as a bi-induced subgraph, you actually forbid one of these special ones as a bi-induced subgraph. And that's true just because every bipartite graph is an induced subgraph of one of these. So if you forbid some fixed thing, you actually also forbid one of these special ones. So forbidding all bipartite patterns as bi-induced subgraphs is the same as forbidding just these special ones, which is why this fake VC dimension is the same as the real VC dimension up to some change in the parameters. Any questions? Okay.
You need some extra vertices on one side so that you can have many copies.
Exactly. Yeah. So that's why you get some extra log. Yeah. Yeah. But it doesn't really matter. Yeah. Any other questions? Okay. Oh, the one final thing I wanted to say, maybe I'll say it here, is that if you don't like thinking about set systems, actually VC dimension you can just think of entirely as graphs. Because given any set system, you can just view it as a bipartite graph, where you put the elements of the universe on one side and the elements of your family of sets on the other side, and you join a vertex on the right to just precisely the elements of the set on the left. I mean, it's literally the bipartite graph whose adjacency matrix is this one. And then the VC dimension of that system is precisely, right, like the neighborhood set system of neighborhoods of vertices on the right to the left is precisely the set system you started with. So really, like, if you don't like set systems, you can just think of neighborhood systems of graphs and VC dimension of graph. It's really all the same. I hope that made things clearer as opposed to less clear, but it's not very important.
But if you have a bipartite graph, you're looking at all neighborhoods, not
Exactly. So so it's not exactly the same, but you can instead work with sort of this. Yeah, it doesn't. Yeah, because the neighborhoods. I mean, you can just look at it. I can define some by neighborhood set system where I just look from the right to the left, and then it's really the same. Okay. So let's do. So if you know anything about VC dimension, you probably know what's called the Sauer-Shelach lemma. So does anyone know who proved the Sauer-Shelach lemma first? Right. So that's the standard right answer. So it wasn't proven by Sauer and Shelach, it was proven by Perlis, but actually it was proven by Vapnik and Turvanenkis even before. Oh yeah, I should have said this earlier. Vapnik and Turvanenkis is what VC stands for in VC dimension. And then it was proven by Perlis, I think in 2 independent papers that he forgot he proved it. And then also by Sauer and Shelach, except Shelach in his paper, it's also in 2 papers of Shelach, and he gives credit to Perlis both times, I think. Anyway, a bunch of people proved this, but really I think it's Vapnik and Turvanenkis, but we call it the Sauer-Shelach lemma. And it says the following, if V has size M, and F is some set system on V, where the VC dimension of F is in most D, then the number of sets in F is at most M choose 0 plus M choose 1 plus dot 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 plus M choose D. So you have a set system of bounded VC dimension. You get a bound on the number of sets in it. It's at most this. This is the precise tight bound, as you can convince yourself without too much work. I will never use this tight bound. I will just use that this is at most, let's say, 2m to the d. And in particular, it's polynomial in M with the exponent d. Okay, so this is a very nice, important result. There's many elegant proofs of it. I think I won't present any of them. So look one up if you haven't seen it before, or ask me. Okay, so this seems great, except it actually doesn't seem that useful. Because I'm telling you, we're focusing on graphs. And like, if I look at a graph, its neighborhood set system automatically has number of sets equal to number of vertices, which is linear in the size of the universe. And that's true regardless of the size of the graph. Somehow, the fact that I get a polynomial bound of like m to the 100 doesn't seem very useful if I already know that there's actually at most exactly n of them. So somehow I don't know, it seems like maybe this isn't very useful. In a moment, I hope to persuade you that even in situations like this, it actually is very useful. So somehow the way you use this is that you can apply it also to subsets of your universe and use that also subsets see only polynomially many sets, sort of when you restrict to the subset. So I will show you a proof using this in a moment. Right, so everyone okay with Sauer-Shelach? Okay, so this is a nice standard basic fact about VC dimension. I want to tell you another one that I think is not quite as well known, but is really important. So it's called Hausler's packing lemma. So let me give you a definition. A set system is called epsilon separated if for all pairs in the set system, their symmetric difference is at least an epsilon fraction of the inverse. And if you think of binary vectors, which you should, this is just like a coding theory constraint. It's that their Hamming distance of the binary vectors is at least epsilon times the size of the universe. So an epsilon separated collection is nothing more than just a code, a binary code of distance epsilon. And of course, we know that in a universe of size n, a code of distance epsilon can have exponential in n, many elements. That's codes of constant rate and constant distance. But the amazing fact is that if you have bounded VC dimension, you actually can't get exponential. So here's the theorem. Maybe I'll write it over here. So this is, it's called Hausdorff's packing lemma. It says the following: if F is a set system, F is epsilon separated, and the VC dimension of F is at most D, then the size of F is not going to be exponential in the size of the universe. It's actually just going to be at most 1 over epsilon to the D, constant over epsilon to the D. So, right, like, in fact, so it's not only just not exponential in the size of the universe, it's actually independent of the size of the universe. And the thing that's really cool, I think this is the first result that to me makes VC dimension feel like a kind of dimension. Because if you think about packing balls of radius epsilon in d-dimensional, let's say Euclidean space or Hamming space, how many of them can you pack? Just for volume reasons, it's on the order of 1 over epsilon to the d. So this is telling you that even though I'm living in potentially a much higher sort of ambient real dimension, if I'm epsilon separated, so I'm packing sort of balls of radius epsilon, and I'm packing them in a like bounded VC dimension kind of way, then it's as though I'm living in a universe that's actually d-dimensional, even though when I look at the problem, it seems to be much higher dimension. So yeah, that's the statement. Everyone happy with the statement?
I know the consequence.
Someone knows. I mean, I think someone knows. I don't know. Yeah. So this is actually highly non-trivial to prove. I mean, there's elegant proofs, but they're really quite clever. I'm going to prove a nearly identical bound that's a lot easier to prove. I'll prove the same thing, but with an extra log factor inside. So I'll prove this. And for all our purposes, this is just as good. I mean, it's nearly the same bound, in fact. But really, all we'll care about is, in the case where d is a constant, which is what we care about, this is also polynomial in epsilon, which is really all we'll need. So both are equally good for our applications.
Is the constant absolutely?
This constant, when I write it like this, it's absolute. Yeah, it's 10 or 1,000 or something. Yeah. Okay, so let me sketch the proof of this. Guys, I don't like that these boards, I don't have room to write on them, but I'll do my best. So proof sketch. Let M be something. So I think the good something is 2 log the size of f over epsilon, but something, some parameter we'll pick at the end. And pick U1 up to UK in V uniformly at random. Just, sorry, K is M, of course. Just pick M random elements in your universe. Let's say with replacement, doesn't really matter. But so each one is independently uniformly random. So then let U be just the set of these guys. And what I want to do is to consider F restricted to U. So the set system restricted to U. What does that mean? It's again easiest to think in this binary sequence thing. I mean, U is just a bunch of columns, right? I'm just going to look at the matrix, the submatrix given by those columns. That's another set system on the universe U. Or in graph terminology, if I have this sort of bipartite graph, I'm just restricting the left-hand side to the subset U. And as both of those perspectives should make obvious, the VC dimension of this restriction is also at most D. Because, I mean, any shattered set of columns would have also been shattered in the original thing. So the VC dimension can only go down when I restrict to a subset of the columns. So by Sauer-Schellach, this implies that the size of F restricted to U is at most 2 m to the D. Because now I'm on a universe of size m, and I have VC dimension at most D, so I apply Sauer-Schellach. Okay? On the other hand, what I claim is that fix, let's say, F not equal to F prime in F. And my claim is that with high probability, F intersect U is not the same as F prime intersect U. So the claim is when I look at two distinct rows up here, that they were different, like they had different entries. Even when I restrict to this random set of columns, I'll still see that they're different. They won't have the same trace on this set of columns. Okay, so we're clear.
You're using that
Of course.
separation.
I haven't used epsilon separation yet, and this wouldn't be true without epsilon separation, but that's exactly where I'm going to use it. Because if you think about it, what does it mean? The probability that F intersect U is the same as F prime intersect U is precisely the probability that for all I, Ui is not in the symmetric difference of F and F prime. Right? The symmetric difference is precisely those coordinates where I can distinguish F from F prime. So failing to distinguish them means that all of my random elements did not come from that set where I can distinguish them. Okay? But this we know exactly what it is. It's at most 1 minus epsilon to the m. Because for a fixed I, we know that this set has size epsilon times the size of the universe at least. The probability that my Ui doesn't fall in it is at most 1 minus epsilon. And they're all independent, so I just get to raise that to the nth power. Okay, and now we use our choice of m, so this is at most the size of f to the minus 2, just because of how I picked my m. So for any fixed set, for any fixed pair, f and f prime, the probability that they become equal when I restrict to u is at most size of f to the minus 2. So I pick my parameters so that I can now union bound over all such pairs. I have at most size of f squared of them. So with positive probability, for all f not equal to f prime, I have that f intersect u is not equal to f prime intersect u, just by a union bound. But that means, if this happens, then that means that the size of f restricted to u is actually equal to the size of f. Right? The size of f, if they're all distinct, then I don't have any collisions. The number of sets I end up with is equal to the number of sets I started with. So what I learned at the end of this process is that with positive probability, my restricted set system has the same size as my original one. But on the other hand, by Sauer-Schellach, it was at most 2m to the d. So if you unpack what all of this means, we've just proved that the size of f is at most 2m to the d, which is by assumption 2 log the size of f over epsilon to the d. Okay, and solving this is a tiny bit annoying because you have the side, like the variable on both sides of the inequality, but you can solve it, and it gives this thing. And the log is coming from that log. But yeah, that's where this comes from. Okay, that's what it is. Any questions? And this proof captures the thing I was saying, that you can apply Sauer-Shelach sort of also to subsets and get something useful out of it.
And the proof of the type bound is it doesn't look like this.
It has portions that are like this, but a much more careful analysis that I could not reconstruct. I mean, it's really quite clever. You can follow every step line by line, but somehow some magic thinking went into it. Yeah, but it's still, you still sample random elements like this. You just sort of do a smarter analysis.
Can you derive like the Johnson bound or something like that for this decoding the style of this statement?
I have no idea. Maybe. Yeah. I don't think, I've never seen someone in like coding actually use this, even though it's like clearly a coding type of statement. But yeah, I'd be interested if there were such thing. Okay, good. Other questions? So maybe I'll go back to regularity and then we'll take a break. So let me just tell you one corollary of Hausler. So this is, I think of as a regularity lemma for set systems of bounded VC dimension. So it says the following: let F be a set system with VC dimension of F being in most D, let epsilon be greater than 0, then here's an example of a partition, which is not necessarily an equipartition. You can make it one if you want, but let's just say partition F into F1 union Fm. Probably should have used a different. Okay, in my notes, I did not use M in this proof. So pretend I used K in that proof. Yeah, so I'm sorry about that. So the statement is that any set system of bounded VC dimension, I can partition into a bunch of pieces where M is the most constant over epsilon to the D, such that for all pairs, for all sets that lie in the same piece, their symmetric difference is small. So it's some sort of regularity lemma or clustering lemma or something. So that any set system of bounded VC dimension, I can cut it up into a small number of parts. Here, small is just polynomial in epsilon, such that the parts are like highly clustered. So all sets in the same part are nearly identical. Their symmetric difference is the most epsilon. So I can chop my sequence, my set of vectors into pieces where each piece is sort of clustered. It's like in a small radius Hamming ball. Okay, so everyone okay with the statements? Okay, and the proof is one line, maybe 2 lines. Pick a maximal, let's say epsilon over 2 separated subfamily F prime inside F. Just pick an arbitrary maximal separated family inside F. So on the one hand, by Hausler's packing lemma, the subfamily is small. Its size is at most this, right? On the other hand, by maximality, every other thing in my family must be close to one of the things in my maximal collection. But then by the triangle inequality, if I have 2 things which are both close to the same thing, they're also close to each other. So now I just do the clustering by putting, I'll have a part corresponding to each thing in my maximal collection. I just put each other set of my family into the one that it's closest to, and I will precisely have this condition. So, I won't write that, but I hope that's clear to everyone.
Some communities people prefer the word epsilon net to an epsilon.
Sure, yes. Yeah, it's the same as an epsilon net, or epsilon over 2 net. Yeah. Okay. Any questions? So finally, let's get back to graphs. So here is finally one corollary of corollary. It is the regularity lemma for graphs of bounded VC dimension that I promised you. So it says the following: if G is a graph whose VC dimension is a most D, then G has an epsilon homogeneous partition, equipartition, into at most constant over epsilon, let's say to the 2 parts. So it's the same as the corollary up there, that a graph of bounded VC dimension can be decomposed so that almost all pairs have edge density close to 0 or 1. But now instead of getting crazy tower type number of parts, we're getting just a polynomial number of parts. And the proof is you apply that result. So look at the neighborhood set system. It has bounded VC dimension. So by this thing, I can cluster this family of sets into these clusters. The sets are in bijection with the vertices. So this clustering is the same as a partition of the vertices. And the property this gives you is you get a partition of the vertices such that any two vertices in the same part have nearly identical neighborhoods, right? They differ only on an epsilon fraction of the other guys. Okay, that's not precisely this epsilon homogeneous thing, but there's an easy double counting argument that shows you that once you have this thing, you've partitioned so that neighborhoods in the same clusters have nearly identical neighborhoods. It's not hard to show that in fact, almost all edge densities are very close to 0 or 1. So I'm not going to show you that. It's clever, but it'll take a little bit too much time. And yeah, maybe I should just say this theorem that bounded VC dimension gives you a partition with polynomially many parts. This was first proved independently by Lovas Segedi and by Alon Fisher-Newman. This proof with this optimal bound, this bound is basically optimal. This proof is due to Fox, and Zug. Okay, and I think we can take a 5-minute break. Oh yeah, sorry, do you have a question?
So for the first corollary, based on your proof, you actually have a stronger condition, right? Because not only within each Fi, you are like the sets are close to each other, but between Fi, they are like they are separated.
That's right, yeah. So it's even stronger, but yeah, I don't know how to use this for anything, but yes. Okay. Each Fi is clustered, and pairwise between them, they're unclustered, anti-clustered, yeah.
Wait, okay. The centers are epsilon like 2 separated, but like you can.
Yeah, maybe you can have 2, but that's right. Yeah, it's probably not true. Yeah, the centers are separated, but the guys in the balls around them might be close. So I think that's right.
Yeah, that's what I mean. Yeah.
Yeah, yeah. Okay, yeah, let's take a break. Okay, operationally, it is the case that there's a large number of theorems in like learning theory and model theory and stuff like this. Like you sort of have a complete dichotomy. Like either you have bounded VC dimensions and something good happens, or you don't, and then like it's the worst case scenario. Actually, I'm going to write a theorem of this nature as well. Somehow VC appears in many of these dichotomies. That it's like either you have bounded VC and then everything's great, or like unbounded is sort of as bad as like it's as bad as it can be. And this somehow in some sense suggests that like this is the only notion that can capture in these kinds of settings, like what it means to be like simple or not simple.
Also, you mentioned VC dimensions with an S in the title. Are there like only are there any more types of VC dimensions?
Yeah. So we'll see more in a minute when we get to when we go to hypergraphs.
Are they like equivalent in terms of whether it's unbounded?
No. So yeah. So somehow when you go to hypergraphs, you actually end up, okay, so I guess this is a counterexample to the thing I just said. When you go to hypergraphs, you end up having many different notions of VC dimension, and they're all non-equivalent, and they sort of characterize different things. So there's going to be sort of a whole hierarchy of different VC dimensions that capture different things. Yeah.
I'm forgetting in the epsilon net corollary, or this corollary up here. Is this also true if you measure with respect to like any weighted distribution?
Yeah.
Yes.
Yeah.
I mean, it's
you don't need to
deduce it. You just deduce it from this statement because if you have another weighting, you can just like duplicate elements based on their weight and then like apply it to the
Okay.
uniform distribution.
Yes, because there's.
Yeah, but I think you can also just like run the same proof. Probably you sample them not uniformly at random, but you sample them proportional to their weight. And
That's
then
what happens in learning theory.
right, yeah.
I'm trying to remember if you needed an extra log 1 over epsilon in the standard learning, right? Because realizable learning, if you just use uniform convergence, it requires d log 1 over epsilon samples, not d over epsilon samples. So I was wondering if the log should.
That I guess I don't
I
know.
think it must be a different. It's like just to get high probability, or like you have the union bound over this.
Plausibly, yeah. Certainly the log in the proof I presented is just coming from this union bound. I accept there's a smarter proof that would get it, but yeah.
Is there a way to phrase this as a potential decrease argument?
Don't know. Maybe. Yeah, I have not, don't remember seeing that, but yeah. If there's a way of phrasing this as like a potential decrease argument.
Where you make more progress than the similarity regularity.
Yeah, somehow not. I don't think so. I think somehow it's genuinely picking up something different. Yeah. Should I start again?
Yeah, I mean, maybe let's call.
Okay.
Here's one, both.
Yeah, so where I want to go in the second half is to hypergraphs instead of graphs. So a ton of stuff are being very different in the world of hypergraphs. So the thing that will end up happening is, regularity gets a lot more complicated, and I'll tell you a little bit about that. Also, it turns out that when you go to hypergraphs, there turns out to not just be one notion of VC dimension, but several. So it's not on K uniform hypergraphs, there's a hierarchy of K different notions of VC dimension, which I hope to tell you a little bit about. And the other thing that starts happening is that this kind of very elegant proof stops working. And the reason it stops working is that for these hypergraph notions of VC dimension, there is no version of Hausdorff backing lemma. So you actually can't run any proof like this. You have to do completely different things. So I hope to tell you about some of this stuff. But yeah, basically, so the story for graphs is very nice, and this proof sort of gives everything beautifully, and you then have to do completely different stuff in hypergraph. But maybe before I do that, let me just tell you about one cute theorem. Yeah, Rahul asked about, I said something vague about how VC dimension is sort of the only notion that you can use. And really what I meant by that is that in many areas of math where VC dimension shows up, there are these dichotomy theorems that either you have bounded VC dimension and something good happens, or you don't, and then you're sort of in the worst case. And I want to give you one such dichotomy theorem for graphs. So theorem is that the following are equivalent for a hereditary family of graph G. Okay, so hereditary family just means closed under induced subgraphs. So if your graph is in the family, then so is any induced subgraph of it. But don't worry about that. Just think about the following are equivalent for a graph G. It's just that to make it into a real statement, somehow you can't. It's this thing we were saying earlier, that it sort of only makes sense to talk about like infinite sequences of graphs. And so you can't really make this make sense for a single graph, but think of it as it does. So first one is G has bounded VC dimension. Second is that G has a epsilon homogeneous partition into poly 1 over epsilon parts. So I already showed you this proof that if you do have bounded VC dimension, you have a homogeneous partition into polynomially many parts. But the converse is also true. It's in fact equivalent to G having an epsilon homogeneous partition into any bounded number of parts. Right, so some graphs, like a random graph, you cannot homogeneously partition into any bounded number of parts. Some graphs you can, and just having a homogeneous partition into any bounded number of parts is equivalent to having bounded VC dimension. So therefore, from any number of parts, you can actually get polynomially many parts. This is in turn equivalent to G has an epsilon regular partition into poly 1 over epsilon parts. Right, so going back to the original Simonyi regularity lemma, I told you that epsilon homogeneity is stronger than epsilon regularity. So the second you have this epsilon homogeneous partition, it's automatically also epsilon regular. But it turns out that just having a regular partition with polynomially many parts is also equivalent to being bounded VC dimension, and therefore, in fact, you even have a homogeneous partition into polynomially many parts. And this is in turn equivalent to G has an epsilon regular partition into any subtower number of parts. So we know that every graph has an epsilon regular partition into a tower type number of parts. If I tell you you can do better than tower type, then automatically you can actually do polynomial because it's equivalent to this bounded VC dimension. And in fact, you get the homogeneous. Yes, right?
The third one, what does bounded number of parts?
Right. So it's again this thing that, I mean, this is for a family, but I mean bounded depending on epsilon. So
tower, for example?
yes, tower, for example. Yeah. But the thing to keep in mind is that like, if you have a huge random graph, it does not have a homogeneous partition, epsilon homogeneous partition into any constant depending on epsilon number of parts. If you partition it into any constant number of parts, you'll still see density 1/2 between all of them if it's really large.
So the point is, suppose I have a partition, homogeneous partition with tower number of parts.
Yes.
It means that there is another partition that's
Polynomial. Yeah, exactly. Yeah. It's crazy, right? It's really cool.
So subtower means what kind of function?
Yeah, so I mean, in fact, sort of just less than Gowers' lower bound, basically. So even tower with epsilon to like a better constant.
You don't actually just get it just from one partition, right? Like
right.
The fact that it's a family, it's really
yes. So of course, because some of this doesn't. This is the thing; it doesn't actually make sense for.
No, I mean,
yes.
I think it's more than just. It's hard to to state it formally. It's like
it's not true.
There's stuff in learning theory, like a lot of times, it's really if you have something that holds for every distribution, that's like a really strong assumption.
That's right. Yeah. So it's along those lines, exactly. Yeah. Yeah. So it's really about having. Yeah, it's about having it for this whole family. Okay, and so having, oh yeah, sorry.
Subtower is that strong that matches Gowers' lower bound?
Yes, yeah, just anything that's better than Gowers' lower bound. Yes. So in fact, despite being seeming like an amazing theorem, the proof is kind of trivial and it gets to Xander's point that I'm sort of a little bit cheating. I'm assuming something very strong. So I've already showed you that this first one implies the other four. I mean, right, I proved to you it implies the second one. That clearly implies the third one. Also, homogeneous implies regular. So second implies fourth, and obviously poly is less than tower. So first one implies the other four. So it suffices to prove to you that negation of the first one implies negation of the other four. Okay, what does negation of the first one mean? It means you have an unbounded VC dimension. So you contain every bipartite graph as a bi-induced pattern. So your family, because it's hereditary, it actually just contains all bipartite graphs as induced, as things in your family. But then, so for example, you'll just have huge random bipartite graphs as elements of your family. So you certainly won't have homogeneous partitions into any bounded number of pieces. Also, it'll contain Gowers' example, the bipartite version. So you also don't have any regular partitions into subtower number of parts. So that's it. So I mean, okay, the point is that like, it sounds amazing, but it's actually a little bit cheating because like, it's what Xander was saying. I'm actually assuming something really strong by having this family. Yeah.
No, first you said, like, ignore this word hereditary.
Yes, yeah, so now I'm saying don't ignore it, yeah.
But now, like, the whole proof is focused.
Exactly,
So,
yes.
Like, is there something where
So,
it's actually...
yeah, so especially with the first two, you can make it without being hereditary, but then you again need to do some sort of distributional thing. So you need to be able to sort of reweight you have a graph, like a single graph, but you need it to be true for no matter how you weight the vertices, you can find, yeah. And you can't really get a statement that involves the regular partitions unless you go to hereditary, as far as I know.
So what's the same? I mean, I don't like this. What's a non-cheating statement?
I was saying that more polite.
I know.
Okay, I mean, there isn't. When I get to hypergraphs, I'll show you other statements of this type that will also be cheating in the same way because they'll have the word hereditary in them, but the statements will be non-trivial in a way that this one is not.
Can you explain what heredity means again?
Just that it's closed under induced subgraphs. So if you have a graph in the family, all of its induced subgraphs are also in the family.
Where do you see the infinites? Or
what do you mean?
I mean, you should have an infinite set of infinite sigma.
Well, somehow everything is trivial if you have only finitely many graphs, because like any bounded number of parts, just take the number of parts being the maximum size of a graph in your family. Yeah. Okay, if you don't like this, I think that's completely fair. And I will simply move on and take your criticism. Yeah. Okay. Right. So let me move to hypergraphs. We want to understand hypergraphs, and we want to understand hypergraph regularity. So I'm going to work with 3 uniform hypergraphs for basically the whole remainder of the talk. So we just sort of try to understand what the natural extensions of the things we did for graphs are. So for example, if we have a 3 uniform hypergraph, we can define the edge density of a triple of parts to be, the number of edges with 1 vertex in each divided by the number of possible edges. And then we can say that x, y, z is weakly epsilon regular. Okay, so you might hope to call it epsilon regular, but we call it weakly epsilon regular because as we will eventually see, it's too weak for some things. But the x, y, z is weakly epsilon regular if for all x prime subset of x, where the size of x prime is at least the size of x. And the same thing for y and z, the edge density between x prime, y prime, and z prime minus the edge density between x, y, and z is the most epsilon. This is the natural extension of the graph definition before to hypergraphs. Right, and then you can write down a regularity lemma. So this was proved by Chung in the 90s, I think. So every free graph has a weakly epsilon regular partition into at most m of epsilon parts. Okay, that's good. It's the same proof as Simoni's proof, more or less. And so her proof also gives that this M is tower type. And you can also just take Gowers' example and turn it into a 3 uniform hypergraph and get a tower type lower down. So far, everything seems kind of the same. One thing that's different is that this notion of regularity does not support a counting lemma or an induced counting lemma. So eventually, I hope to prove this to you. It's actually quite simple, but I'll get to it eventually, which is why we call it weak. It's too weak for many applications that we would like to use it for because it doesn't support a counting lemma, which is the kind of thing we want to use regularity for. Okay, great. So, of course, our next goal, nevertheless, is to try to understand this notion and to see what is a good definition of VC dimension that will allow us to both qualitatively and quantitatively strengthen this. And so I think the definition you would come up with, if you think about it enough, is, so first of all, I guess there's many people here who like links. So the link of a vertex V and V of H is the graph whose edges are all pairs xy such that Vxy is an edge of H. Right, so the link of a vertex is like its local view of the hypergraph, which pairs it lies in to form hyperedges. And then we can define the neighborhood set system of H to be just the set of all links of vertices. Just like before, we defined it to be the set of all neighborhoods. This is a natural extension. And then we can define what
It's a family of graphs.
now it's, yeah, so now this is a family. Yes, that's a good point. It's a family of all, it's a family of subsets of pairs of vertices. Yeah, so it's a family of graphs on the vertex set. That should be V of H. Exactly. And then we can define the strong VC dimension of H is defined to be the VC dimension of this neighborhood set system. Good. And then here is the theorem that you hopefully expect. So it proved independently by Chernyakov-Starchenko.
You treat each LV as a subset of edges and
Exactly. Yeah. So it's a set system defined on the universe is all pairs of vertices. Exactly. So the theorem that was proved independently by Chernyakov-Starchenko and Fox-Batsuk is that if H has bounded strong VC dimension, then H has an epsilon homogeneous partition into only 1 over epsilon plus. So I guess I haven't defined epsilon homogeneous for hypergraphs, but it's exactly what you expect. Almost all triples, I see edge density close to 0 or 1 between them. Okay, so the point is that this theorem qualitatively and quantitatively strengthens Chang's regularity lemma. Qualitatively, we go from tower to polynomial number of parts. Sorry, that's quantitatively. Qualitatively, we go from this weak epsilon regularity to this epsilon homogeneous thing, which is stronger. Okay, and the proof is the same as that proof. It's like literally the same. You again apply this clustering lemma to these links. So you get a partition of the vertices such that all pairs of vertices within the same part have nearly identical links. And then you check that that implies this, which I also didn't do that in the graph case, but it's a very similar proof. Yeah.
Are these all limited to 3 graphs or?
No, so this works exactly the same way for K uniform hypergraphs.
Both theorems.
Yes, yeah. I will hopefully say a little bit about how to uniform these later, but things are complicated enough for 3 uniform hypergraphs. Okay, so far they don't seem complicated at all, but I promise we're getting there.
So you said that your definition of strong VC is the dimension of the worst link?
No, it's the dimension that we'll get to in a minute. It's the dimension of this family. So you run over all vertices, you look at their link as a subset of the possible edges, so a subset of possible pairs. So now you have a family of subsets whose universe is all pairs. It's the VC dimension of that family. So it's maybe good to say, another way of thinking about this is it's also defined in terms of shattering. What you're shattering now are pairs. So maybe I'll do it here. So having the strong VC dimension at least D means you have a collection of pairs and you shatter them in the sense that for every subset of them, there is a vertex that forms an edge with that one, forms an edge with that one, but does not form an edge with that one. And for every subset, you do this. So that's exactly what this means.
What do you say strong?
Because soon we will get to new notions of VC dimension. So actually this used to just be called the VC dimension, but this is the strongest, saying this is bounded. There's a whole hierarchy of VC dimensions, and this one being bounded is the strongest of them. So yeah, this is not really standard terminology, but it's the best one that I've been able to come up with. Okay, good. Any other questions? So we'll state another theorem that Eric won't like. So theorem, this is due to Terry. So I'm giving an attribution on this one. So this one doesn't, this was first observed in a paper of Alon Fox Zhao, I think, but somehow I don't think they even really claimed it as a theorem because it's kind of dumb. This is a real theorem. And what Terry proved is that the following are equivalent, again, for a hereditary family of hypergraphs now. But one is that H has bounded strong VC dimension. Two is that H has an epsilon homogeneous partition into following 1 over epsilon parts. And three is that H has a weak epsilon regular partition into, again, following 1 over epsilon parts. But the other two bullet points are not true in this equivalence. So even if you think I'm cheating with the hereditary family thing, even with that, this strong VC dimension characterizes when you have a homogeneous partition into polynomially many parts. It characterizes when in Chung's regularity lemma, you can go down to polynomial, but it does not characterize when you have a homogeneous partition into any bounded number of parts. It does not characterize when you can do at all better than Chung's regularity lemma. So, okay, I mean, you can still claim that I'm cheating because of this hereditary thing, but like this is a genuine difference from what we saw before.
Meaning there are examples that show.
Yes, so let me show you an example, which is due to Terry, which is a really nice example. So what the example will be is I'm going to have a tripartite thing, parts A, B, and C. I'm going to chop A up to A into A1 up to AK and B into B1 up to BK. These are just partitions. And then for each I between 1 and K, I pick Ci, a subset of C, at random. So for each index I just pick a random set inside C. So maybe that's C1, and that's C2, and so on. Just random sets. And then my hypergraph, so the edges of my hypergraph are just going to be the union from I equals 1 up to K of AI cross BI cross CI. So the edges are every vertex here, along with every vertex here, along with every vertex in the C1, that's a triple, and that's it. I mean, except for all K. Okay, so the property that this thing has, okay, first of all, maybe I'll say it like this. It does not have bounded strong VC dimension. And the reason is, I mean, it has strong VC dimension of at least K. And the reason is that you can shatter a set consisting of a vertex, like your pairs that you're shattering will be like that one, and that one, and that one, and that one, and that one. And right, like there will be some vertex, because these sets are random and this thing is very large, there will be some vertex that's in any specified collection of the CIs you want. So it will precisely shatter that sequence of pairs. But the thing it does have is, so H has a homogeneous partition into at most 2 to the K parts. The reason is the homogeneous partition will just be take the common refinement of all of these CIs, just take the Venn diagram they define, and just partition A and B into just these pieces. And then it's obviously homogeneous, right? Because just all the vertices actually fully complete are empty on every triple of parts, right? Like if I take a vertex from A1, a vertex from B1, and a vertex that lies in one of the Venn diagram cells corresponding to C, that will be, for C1, that will be complete. If I take a vertex in a partition corresponding to the complement of C1, that'll be fully empty. So this is a homogeneous partition, but you can show that it does not have a homogeneous partition into any sub-exponential number of parts. I'm worried that's saying something a tiny bit wrong. Sorry, I should. Sorry, I should have said something very different. I apologize. Okay, I'm sorry about this. We want to set k to be 1 over epsilon, and then into 2 to both 1 over epsilon number of parts, but no smaller. So this is something you have to prove. But this example, if you partition it into a sub-exponential number of parts, no matter how you do it, sub-exponential and epsilon, some triple of parts will have edge density basically 1/2. And the reason more or less is that sort of if you partition the C into a less than 2 to the 1 over epsilon number of parts, one of those parts will just be intersecting more or less all the CIs, or like a constant fraction of them, non-trivially, and then you'll have edge density that's bounded away from both 0 and 1.
The next thing here is how did the fact that you have hypergraph versus a graph be useful? How is it useful?
Good question. I'm not sure that I have a really amazing answer, except that somehow this example doesn't, if you try to do it in graphs, it won't work.
If we would try to do it in graphs, we just use A1 to AK without the B's.
Yeah.
In a graph, it will be a random graph.
Yeah, so you just get basically a random graph.
I mean, it's not exactly, these A's are chunks of.
Yeah, but it's like a blow up of a random graph.
Blow up of a random
Yeah.
graph.
And I think this is, I think I want to think some more about how to answer this question. Yeah, I think it's a good question. I am afraid that I don't feel like I have a great answer right now.
Sorry, but actually, like, this thing doesn't have bounded VC dimension, nor in the graph case, right? Like,
That's right, yeah.
The point is what, that in the graph case, to partition this, you would need somehow a tower to.
What I'm worried about is that I tried to simplify Terry's example, and I'm worried I simplified it so much that I said something wrong. Because you raised good points about how this should be working in the graph case. And so perhaps,
Maybe we can skip forward.
yeah, I think, yeah, I'm sorry, but I think, yeah. It's a very good question, and I'm a little confused. Yeah, sorry. Yeah, any other questions? There are allowed to be hard questions that I can't answer. Okay. So the question now that we want to answer is there something that does characterize, for example, when you have a homogeneous partition into any bounded number of parts? And the answer is that there is, and it's in fact the thing Xander asked about. So this is a new definition. So definition, the VC1 dimension of H is the maximum over all vertices of the VC dimension of the length of V. So basically, this is another reasonable notion for what it means for a hypergraph to be kind of simple, is that when you look at every link, you see something simple. Like you see a graph of bounded VC dimensions. And so the HDX, yeah.
This we cannot do for graphs.
Yes. Yeah, so somehow it's like if you like HDXs, this is kind of, you want to think of the hypergraph. You can understand it if you can understand all the links in some good way. So this is the definition. Another way of thinking about it is somehow this notion of shattering didn't really use that we were in a hypergraph. And this is equivalent to shattering a collection of pairs that looks like this. So it's the same shattering condition that for every subset of the pairs, you have another vertex that forms an edge with exactly that subset. But now you're not shattering just like a completely arbitrary collection of pairs, you're shattering a star. So it's a shattering condition which has a graph theoretic meaning. The theorem, a theorem that was proved independently by Tausner and Terry and Wolf, is that if H has bounded VC1 dimension, it has an epsilon homogeneous partition into some bounded number of parts, some M1 of epsilon, many parts. So this is having bounded VC1 dimension is a weaker notion than having bounded strong VC dimension, but it's still strong enough to guarantee a partition into a homogeneous partition with a bounded number of parts depending on epsilon. So this is somehow, this shows you that the strong VC dimension, I mean, it's not the be all end all for this homogeneous partitions. Unfortunately, so this again allows us to qualitatively strengthen. Oh yeah, sorry, do you have a question?
Why is this weaker than that one?
The reason it's weaker is that here I allowed you to shatter an arbitrary pair, an arbitrary collection of pairs. Here I'm requiring that you shatter a collection of pairs that form a star. So if you do shatter a star, then you certainly shatter that collection of pairs, but not vice versa. Yeah, so here I drew them as disjoint, but really the definition allows them to be an arbitrary collection of pairs.
Do you not get this for free? Like you just take this and
no, you don't get this for free
because there's no count.
Yeah, so somehow it just doesn't work. And in fact, so as I said, this is a qualitative strengthening of Chang's regularity lemma under bounded VC1. Not only is it not a quantitative strengthening, it actually got worse. So Chernikov and Tausner proved this with infinitary techniques. They didn't get any bound on this M1 of epsilon. Terry and Wolf did get a bound, but Terry and Wolf proved that this M1 of epsilon is at most the Wouser function of some polynomial in epsilon. So the Wouser function is the next level up in the Ackermann hierarchy. It's this iteration of the tower function. So it's a tower of tower, like it's tower of twos, whose height of the tower of twos, whose height of the tower of twos, and so on. All the epsilon we have. So like we've strengthened it qualitatively, but we've actually weakened it quantitatively. And in particular, you don't get it for free from Chang. Okay, but it raises the question of, can you do better? And this was first done by Terry. So a few years later, Terry proved that this M1 of epsilon is at most double exponential in poly 1 over epsilon. So suddenly much better. So it is a quantitative strengthening. And she conjectured that this double exponential is the truth. But actually, one thing we proved with Lior and Asaf is that actually it's at most single exponential, which is actually tight because Terry's example that I may have screwed up shows that you do need a single exponential lower bound. So so in fact, this bounded VC1 dimension allows you to strengthen Chang's regularity lemma to get a homogeneous partition, and therefore a weakly regular partition, of a bounded number of parts, even single exponential, not polynomial. Single exponential is the truth. And in fact, maybe I won't write it fully to spare you the time, but there is one of these characterization theorems with all 5 bullet points. So this VC1 dimension does characterize when you have homogeneous partitions of any bounded size, which is equivalent to having them of at most exponential size. That's equivalent to having regular partitions, weakly regular partitions, of at most exponential size, which is in turn equivalent to having weakly regular partitions of any sub-tower number of parts. So this notion is precisely the thing that characterizes when you can improve Chang's regularity lemma, either quantitatively to anything sub-tower or qualitatively to homogeneous.
If the D of the VC dimension
It's hidden in the poly, exactly.
Like 1 over epsilon to the D.
Yeah, I think we got something worse in our proof. We didn't really try to optimize it, but yeah. But I mean, it'll epsilon to the D to the 10th maybe, but yeah.
Are we all the time in 3 regular, in 3?
For the moment, yeah, but actually all of these things work also in higher uniformity.
Then instead of M1, we need something else.
So the thing you want to do is you want to look at if you're in K uniform hypergraph, you want to look at the joint link of K minus 2 vertices. You pick K minus 2 vertices, you look at the graph that is their common link, you look at the worst of those, that's the thing, and that characterizes homogeneous partitions, and again, it's just single exponential. Is the bound.
Something to the power of K?
I mean, this poly will also hide some dependence on K, but for any fixed K, it will also be single exponential in some polynomial in K. Yeah. Some polynomial in epsilon.
Yeah, this VC1 dimension related to this works of Rogliano and Maliaris.
I mean, yes, in some sense. So the thing I'm about to talk about, which is what's called VC2 dimension, is the one that really comes from model theory. So this one was actually introduced independently by these people, like 2016-ish, because it really comes naturally from this hypergraph regularity perspective. The thing I'm about to talk about, this VC2 dimension, was defined by Shelach in the 90s, because that's the one that actually captures model theory, model theoretic things. Yeah.
Can you say again, what's the relationship between these two notions of VC?
So this thing being bounded is strictly stronger than that one being bounded. Any questions? Okay. Yeah, we'll move on and talk about VC2 dimension, which is somehow sort of the most interesting in some sense. But any other questions? Okay, so if you go back to the very beginning, when I defined VC dimension for graphs, I did it in this fake way, which is that the fake VC dimension is just whether you exclude some bipartite graph as a bi-induced pattern. If you think about hypergraphs, there's an obvious correct generalization of that notion to hypergraphs, let's say 3 uniform, which is forbidding some 3 uniform tripartite thing as a tri-induced subgraph. So that's the definition. So yeah, H has bounded VC2 dimension if there is a fixed tripartite regraph. Again, I'm just in uniformity 3, T that is not a tri-induced subgraph of H. And tri-induced means, again, what you think it should mean. So the edges, so you have, edges across, the triples do appear, the ones that are not supposed to appear do not. And I don't care what happens for edges sort of entirely inside or that are, let's say, 2 vertices in one part, 1 vertex in the other part. So I just care about sort of the transversal edges. Okay, so this is a definition you can write down. It also has a shattering notion. So you can also define it in terms of shattering. Here, what you are shattering is, so this is equivalent to shattering like a KDD. So now the collection of pairs you want to shatter is not an arbitrary collection, and it's not a star, it's a complete bipartite graph. No, I got that one already.
You define shattering, I mean, not shattering.
Yeah, so sorry, yes, not shatter, yes, exactly. Yeah, so you do shatter this if for every subset of the pairs, you have a vertex that completes an edge with exactly that set and not the other ones. If you think about it, that is just saying you have a tri-induced copy of some 3 uniform tripartite hypergraph. It's the one that has d vertices on one side, d vertices on the second side, and 2 to the d squared vertices on the third side. And just what you have is that the 2 to the d squared are indexed by subsets of the d squared edges here, and they're connected to exactly the ones that they're supposed to be connected to. So this is equivalent to not shattering one of these guys. Make sense? Okay. So I think this is a natural notion for a bounded VC something dimension. And the question is, what is it good for? And the answer seems to be not much. So I will show you what it is not good for. So maybe I'll give you an example first of all. What do these things look like? So the example is take any graph G. Let's assume for simplicity that G is tripartite. It doesn't really matter. Let's say. It really doesn't matter. Take any tripartite graph G, and then let H be what we'll call delta of G, which is the hypergraph of all triangles. It's the hypergraph whose hyperedges are just all triangles in G. It's the Clique complex, the 3 uniform Clique complex of G. And the claim is that no matter what G is, this thing always has bounded VC2 dimension. So this thing has VC2 dimension, actually at most 1. Okay, always, doesn't matter what G is. And the reason is super simple, because there's no tri-induced copy of, let's say, K2 minus an edge. So this is some tripartite hypergraph. And it's the one with 2 vertices, 2 vertices, 2 vertices, and 7 out of the 8 possible edges. That thing will never appear as a tri-induced subgraph of this. And the reason is, think about it, what does it mean for the 7 edges to appear? That means that so once you know that these 7 triangles are all triangles in the graph, all of the pairs joining 2 of the vertices must be edges of the graph, but therefore the 8th triangle would also have to be a hyperedge of the hypergraph. So you don't get an induced copy of this. Right? So this gives you a huge, very robust family of examples of hypergraphs with bounded VC2 dimension. And this example can be used to do a ton of stuff. So let me just show you some of the stuff you can do with it. So here's something you can do. So bounded VC2 dimension does not imply homogeneous partitions of bounded size. So the previous notions we've had have allowed us to get these homogeneous partitions of bounded size. Bounded VC2 dimension can't give that to you. The reason is just take your G to be a random graph, say a random tripartite graph. So then this H you get out of it will have bounded VC2 dimension, always, but it won't have any homogeneous partitions because no matter how you chop this random graph into pieces, you'll see the same density of triangles among the pieces. So certainly this is true. Another thing you can learn is, let's see what, another thing you can learn is that bounded VC2 dimension does not imply sub-tower bounds in Chang's regularity lemma. So this Chang's regularity lemma, you cannot improve its quantitative dependencies under the assumption of bounded VC2 dimension. And the reason is, just take this graph to be Gowers as example. The hypergraph you get will again have bounded VC2 dimension. And it's not hard to check that if you had a regular partition of this hypergraph, that would correspond to a regular partition of Gowers' graph. And we know that Gowers says you don't have subtower partitions.
We expect to have a partition of the edges rather than the vertices.
Great. So I'm going to get to that in a minute. Yes, but I will say two more things you learned from this before I do. Another thing you learn is that there is no Hausler's packing lemma for VC2 dimension. So this is something I said way back when, but the difficulty in doing this stuff in hypergraphs is that that this Hausler's lemma, which was really the key to doing these partitions in graphs, just isn't true in these other notions of VC dimension. So what I mean by this is, again, take this graph to be random. The hypergraph you get out of it will have bounded VC2 dimension. If you wanted some kind of Hausler's packing lemma, you would want to say that you can cluster the vertices into a bounded number of parts such that their links are very close. They have almost the same length up to epsilon. But in this random thing, that just won't be true, because distinct vertices, their links will differ on quadratically many pairs, because it's random. This bounded VC2 dimension just isn't strong enough to get some kind of Hausler's packing lemma. Even if you forget about polynomial bounds, like you just can't get any kind of bound depending on epsilon. The final thing that you learn from this is, I don't know if the final, but another thing you learn from it is there's no counting lemma for weak regularity. So this is something I said back when I introduced weak regularity. I said that it's too weak to support an induced counting lemma. And this is an example. So if you take your graphs to again be random, let's say random with density 1/2, then the hypergraph you get will be weakly epsilon regular with this definition. Because no matter how you would restrict to 1% of the parts, you'll still see the same density of triangles as you did globally. So it will be weakly epsilon regular, but there can't be an induced counting lemma because I said that there is no induced copy of this thing. So this is the problem with regularity. Yeah.
What's the relation between VC1 and VC2?
So again, bounded VC1 implies bounded VC2, but not vice versa.
Okay, so VC2 is a weaker.
Yeah, exactly. Yeah. Yeah, exactly. Other questions? Okay, and so as Eric was saying, what all of this teaches us is that this is not the right notion of hypergraph regularity. The right notion of hypergraph regularity needs to be able to see the fact that a hypergraph can be defined in terms of a graph. Somehow, like, if the only thing you want to allow yourself to do when doing hypergraph regularity is just sort of look at vertex sets, you won't see the fact that here what's hiding underneath is a graph structure. And like the reason you don't have this K22 minus an edge is because there's an underlying graph. And the hypergraph regularity lemma needs to be able to see this. So I won't state the hypergraph regularity lemma for you because it's super nasty and it's quite difficult to state, let alone to prove. But roughly speaking, what the hypergraph regularity lemma says is that any hypergraph, you can chop up its vertices into pieces. You can then also chop up the pairs into pieces in such a way that the triples, the edges, sit in some sort of quasi-random way over this partition. So with respect to both the partition of the vertices and the partition of the edges. And the upshot of that is that it does allow you to get, for example, an induced counting lemma. So that's the thing that it's good for, because it somehow deals with this fundamental issue that you need to be able to understand if there's a secret graph hiding under your hypergraph.
When I give credit.
Yeah, sorry. Yes. So this was done independently by Gowers and by Rudel and various collaborators, and then also by a few other people in sort of the early 2000s in various sequences of works. And there's actually many different ways of formalizing this thing I'm not talking about. And the different notions have different advantages and disadvantages. So it's not like people independently discovered the same thing. They actually independently discovered different versions, each with its own advantages and disadvantages. And yeah, I won't say any of them because.
Can you say, like, even if you ignore the partition part, like, what is the definition being used just for a hypergraph to be pseudo?
Yeah, so the simplest one, which is the one in this Rudel et al. Thing, is that you have some sort of triple and you have this graph that it's sitting on. So no matter how you restrict the graph to a subgraph in such a way that you keep an epsilon fraction of the triangles, the number of edges you're seeing sort of sitting on that subgraph is, the density is close to what it was before. Yeah. Okay, so maybe I have just 5 minutes, so I won't say too much about this. Let me just say, once you have hypergraph regularity, it is not too hard to show that bounded VC2 does imply sort of some, maybe I'll call it like relative, or let's say epsilon homogeneous partition of vertices and pairs. So we saw that bounded VC2 dimension does not imply that you have homogeneous partitions of the vertices. But once we've expanded our notion of partition to be partitions allowing both to cut up the vertices and to cut up the pairs, then this bounded VC2 dimension does allow you to get sort of a homogeneous version of this, where the edges of the hypergraph sit with density close to 0 or 1 over the graphs you see in this partition. And that's not very hard. So this is like a qualitative strengthening of the hypergraph regularity lemma under bounded VC2 dimension. And in fact, it shows you that this robust example is somehow the only example, right? Because what does it mean if you have a partition into a bounded number of pieces so that you see edge density basically 0 or 1 over all the graphs or almost all the graphs? It means that your hypergraph was actually defined by taking maybe one graph or maybe a bunch of graphs, and just the hyper edges are just all triangles in this, or sort of triangles with 2 edges from this graph and 1 from this graph. But somehow all hypergraphs of bounded VC2 dimension up to some noise look like this example. They come from graphs in some way. The other thing I want to say is that the hypergraph regularity lemma doesn't invoke tower type bounds. It invokes these Wowser type bounds, which are even worse. And Moshkovitz and Shapira proved that Wowser type bounds are necessary for the hypergraph regularity lemma. So it gets really bad. But you can again ask, does this VC2 dimension allow you to quantitatively improve the hypergraph regularity lemma? And that's something we proved. Also a theorem of ours is that bounded VC2 implies tower type bounds in hypergraph regularity. And in fact, tower is necessary. And this is really capturing the same intuition that hypergraphs of bounded VC2 dimension, they somehow look like graphs. They come from graphs. And also the quantitative aspects of the regularity lemma are not Wowser like it is for hypergraphs, but tower like it is for graphs. Questions about that?
Do you get both together, tower type with epsilon one?
Yes, with epsilon homogeneous, yes, indeed. Okay, and in the last minute, I will just out loud, without writing anything, tell you what happens in higher uniformities. So in higher uniformities, you will get k different notions of bounded VC dimension. So there's this strong one, which is the strongest one. It works exactly the same. The weakest one is what's called VC k minus 1 dimension, which is exactly like this. So you would have some k-partite, k-uniform thing that is not a k-induced subgraph. That's the weakest one. And then you have all the intermediate ones, where what you can do is you can look at the link of one vertex and look at, that's like a k-1 uniform thing. Look at its sort of k-1 uniform VC dimension. If that's bounded, then sort of this is a strictly stronger notion. You can look at the links of 2 vertices, joint links of 3 vertices, and so on. So you'll get k different levels in this hierarchy. Each is strictly stronger. There's also a hypergraph regularity lemma for arbitrary uniformities. And as you would expect, you now need to partition the vertices, the pairs of vertices, the triples of vertices, up to the k-1 tuples. Chernikov and Tausner proved like a qualitative strengthening of the hypergraph regularity lemma, which is that if you have bounded VCL dimension, then in this sort of big complicated partition, you're homogeneous above level L, which basically means that these hypergraphs of bounded VCL dimension look like L uniform hypergraphs. They come from L uniform hypergraphs in the same way that these guys came from graphs. But their proof didn't give any bounds, so the bounds for the hypergraph regularity lemma are on the kth level of the Ackermann hierarchy. So for 4 uniform, it's like the iterated Wouser function. For 5 uniform, it's the iterated that thing. And that's necessary. That was also proved by Moshkovitz and Shapira. What we proved is that also the quantitative aspects drop to the Lth level of the Ackermann hierarchy, which is necessary. So also with respect to the quantitative stuff, like you look like an L uniform hypergraph. Okay, and it's 12:30, so I'll stop. Thanks for listening.
You wowed us. Okay, well, thanks again.